Hello everyone and welcome to another class of Finite Element Analysis Laboratory. Now we are finished with the answers module and we are heading into the MATLAB module of the experiments. So the first one is a one-dimensional bar element where you have to do a structural analysis, basically a displacement calculation. So what I have here is a one-dimensional bar element of length 30, that's 90 mm, and it is already given here is already divided into 4 nodes of 3 elements, having a force that is applied at node 2 in the positive x direction of 3000 newtons, and they are fixed at the first and the fourth node. Okay, so you are very familiar with this kind of problem. You would have done a lot of FEM problems using hand calculation this way. Now we will try to do the same thing in MATLAB. Okay. Now in very simple terms, MATLAB is kind of like a mathematical calculator or a matrix calculator basically. So you can in reality just do a copy paste of whatever you write manually, you can just do the same thing in MATLAB as well. Okay, that is the simplest way to do it. Now for decreasing the time consumption, you will create something called functions. You will have scripts so that you can very easily do these calculations, and repeatability is much more ensured. Okay, and some portions of these MATLAB codes that I'm going to show you, you might not be able to comprehend now. Just know that these are available. You can go through them at a later date, but just know how they work. Okay. So without further ado, let's get into the MATLAB and then try to see a comparison. Okay, so I have already loaded up MATLAB and also inputted the codes for the particular problem. Okay, now I'll explain to you from where I took this problem and what is all available at the end of the video. So basically for this problem, what you're doing is, let me go to the, or let me just open it side by side so that you can get a much more better understanding. Okay, so if you have not used MATLAB before, please go and try out any basic MATLAB course which is already available at MathWorks Academy, and then come back to this, because you will have to understand what are all these windows and boxes you have available. Okay, so basically this is your question. You have a element here of Young's modulus and an area of 1 unit square. It can be centimeter, millimeter, it doesn't matter, it's just one. It's one dimensional, right? And these are things that is told. Every element is 30 mm. We have divided. We have 3 elements and 4 nodes. So generally when you do a normal calculation, one thing that you will do is you will find the shape function. If you remember, right, you will find something called n1, n2 if it is required. You will calculate the shape functions. This also will be doing. And so after that, you will find something called your element stiffness matrix. So K you will find for each element. So you have 3 elements here. You will find K1, K2 and K3 using the formulas AE by L, where A is 1, E is given to you here. L is the length of each of the elements. So it will be K1, L1, K2, L2 and K3, L3. And using this you can calculate the stiffness matrix. Okay. Now this formula that you have, that I have given here, okay, which you use for your manual calculation, is the final form that you arrive after a particular derivation. Okay, so using your shape functions n1 and n2, you derive this formula basically to calculate the stiffness, and from the element stiffness matrix you can calculate the global stiffness matrix, where you add in all these 3 along the diagonals. I hope you know all that process. Okay, so like I said, this was derived from a particular integral equation. And in this particular MATLAB, what I have used, or what this book has followed, is basically the equation from this integral. Okay, how they have solved it there. They did not use this. You can do it this way. It is possible. I believe in the manual coding that I have given you, they would have used this method. But while using this, it would be much more longer, whereas this integration method will be much more shorter. Okay, that is the only difference here. So yeah, so you'll find the element stiffness, go find the global stiffness, and finally using this equation ku is equal to f, and in that also we know u is going to be our deflection matrix, and since here u1 and u4 are fixed, you won't have any reactions here, so only u2 and u3 will have some kind of deflection. And on node 2 you have the force, so f2 alone is 3000, all others are 0. Okay, and basically when we do it manually, you would have written ku is equal to f. You'll substitute all the values, and then you will maybe write an equation consisting of u1 plus u2 plus u3 and so on and so forth is equal to f something you will write. You'll find two equations and you'll find u2 and u3 basically. Right, so this is what you usually do. Typically, in reality, what you're doing is f divided by k, or f times k inverse is what you're doing. Okay, quite simply. So this is also what we'll be doing here, albeit in a different way. So I'll explain things in as simple as possible. The ones which require much more complex understanding, I'll skip, and you can go through them if you want, but just know how they work. Okay, so I'll just go to MATLAB. So basically from the same thing I have written what, ignore all the green color. Okay, green colors are commented out, so they are just for your understanding. I will share this code with you, you can go through that as well. Okay, so these are commented out, they are just to understand what the following line is going to be. So you have Young's modulus of 30 E6 area, they just written EA here for easy to understand, and then length of the entire element, which is 90. Okay, so we are assigning the number of elements to be equal to 3, and then we will find out what are the node coordinates. Okay, so we have 4 nodes, right? So you can find that very easily using this linspace command. So linspace command basically has these 3 input arguments. It can have just 2, but it can take in 3 also. Basically this is like the starting of the element's length and the ending of the element's length, or whatever the bar be, and how many divisions that you want basically. Okay, so that is linspace. Just to show you an example if you want, let me say A is equal to linspace of let's say I have a bar between 0 and 0 and 10. Okay, a starting point and my ending point, and let's say I want to divide it into 5. Okay, so if I give that and hit enter, see I divided that into 5 different nodes. Okay, so that is possible. So we'll find out the node coordinates and assign them as xx. Okay, and then we'll also calculate the number of nodes. Now number of nodes is easy, since we already know the node coordinates, we just need to find its size, that's all. Okay, so with that we'll find the node coordinates. Now why have I given 2 here? Okay, so basically size is a function that will require just one, only one input is required. But if you let's just see what happens if I hit size and then this A. Okay, then you'll be able to understand. See, I got 1 and 5. So basically it's a 1 by 5 matrix, and that is the answer it is giving. Size is basically giving the size of the matrix that I have, or array that I have. This is a 1 by 5 matrix or a 1 by 5 array, and that's why it's showing like this. I do not need this, I only need the size of my how many number of nodes are there, I just need to count them. So that is actually available in this second dimension, okay, not in the first dimension. So instead of giving like that, I can give A, comma 2, which is the second dimension. So I will only get the number of nodes as 5. Okay, this is just from the example I showed, that's all. So here the number of nodes will be 4 that you calculate. And okay, so to create the different elements as a matrix, you use this step here. You can try it out as well. If you want, I can just quickly show you what happens when this is done. I can just copy paste this and I will show you. Okay, so they just given II as numbers leading from 1 to the number of elements, which is 3. And they are told first column to be this II and second column to be II plus 1. Okay, so if we give element nodes as my matrix answer, see you will get 1 2 3 2 3 4. So this is 1 2 3 is this line basically, and 2 3 4 is this line. Okay, so this command actually tells you the first column here and the second column, sorry, the first row and the second row. Okay, so that is done here. And then displacements, forces and stiffness. So displacements we just saw in our Word document, right? So in our Word document we just saw displacement. We have 4 displacement, we have 4 forces. They have not assigned the values now, so just to say that there are these many elements, you just assign them as 0. Okay, and with the number of nodes, which is 4, right? So 4 nodes and only 1 row you need. Okay, so it'll be let's just okay, we can't check it out now. Maybe from here we can check it out. Let me copy. Okay, see, you create something like this. So similarly for force and stiffness also, and now you apply the force at point number 2, which is 3000 newtons. Okay, now for the calculation of this particular stiffness matrix, here as you can see they are directly calculating the system stiffness matrix. Okay, they just finish the whole thing here itself, that's all. Okay, but whereas if you're taking manual calculation, or if you're going for a element wise stiffness matrix calculation, it will be much more longer. Again, I'm not going through this because this is a formula you're not familiar with. It's called the central Gauss point quadrature formula. Okay, we are not familiar with this, you would not have learned this also, but to make things easier they have used this. You can Google this particular formula. It's called the Gauss point quadrature formula. Okay, if you go to that, there are different schemes. This is a central scheme that they have used. There are many other schemes. You can basically use that and find what is my system stiffness matrix in just one simple code here. Okay, one simple for loop. Okay, so go through that, you can understand about that. And in this also, see, there is a function here. They are called shape function L2. Okay, now the shape function L2 is basically just to calculate this shape function. You remember, right? N1 and N2. So you will have to create a separate script for shape function. Okay, here, which returns the values of shape and the natural derivatives. This you remember, I think you might remember. It will be, I think it will be something like 1 minus zeta, and N1 will be 1 minus zeta by 2, and N2 will be 1 plus zeta by 2, or whatever notations you had used. Okay, so using those you will be returning, if shape function 2 is called, you will be returning these two values, shape and the natural derivatives. Okay, so with that you calculate the global stiffness matrix. Then you give all your boundary conditions here. So boundary conditions, right? If you take the displacements, they are supposed to be 0 0 here, and these two only will have values. So those conditions you will give here. Okay, like those are the the free degree of freedom. Okay, because those two are fixed, right? So we'll have to do that. And then finally, for the solution process, it's quite simply, like I said in the Word document, you will have to do a matrix division by F and K. Okay, so F divided by K, this inverse division you will have to do, and that is also written as a separate function called solution here, as you can see. So in this particular function you have created called solution, you will be calculating all your stiffness, your displacement. Okay, so stiffness and displacement is calculated here. See, it's just a division. Okay, so you're just dividing it by the force to calculate it, and you will be able to find what is my stiffness. I have not included any stress values here. You can do that later also, but this is typically how you solve it. And finally, just to see all the answers, I just wrote down displacement, stiffness, number of nodes, and prescribed DOF, and you can calculate them. Okay, we have actually calculated stiffness here. Yeah, we have stiffness here. Like, we didn't calculate the stresses here. Okay, so I didn't include any stress calculations here. You can include them here after this is over also. Okay, so let me just clear the command window, and let's run the program and see. Okay, let me clear all as well. Okay, so just remove all the workspace values and let me run the program. Yeah, so basically I can get my displacements u2 and u3. Okay, so this is the degree of freedom, right? 1 and 4 are fixed, so that also we had defined. So 2 and 3 you will get the values. This is your global stiffness matrix with 4 nodes. And okay, I unknowingly called that one more time, so that's why it came here. Okay, so that's how you do a one-dimensional bar element. And similarly, all the other experiments also you can do it pretty easily using MATLAB. And in the manual that we have provided for you, there will be a different code available. This will not be the code. It will be a much more longer code. And why it is because it will be using a different method to solve the stiffness matrix, and also the output will have images basically. Okay, so like how we can see the deflections in ANSYS, maybe not as beautiful as what you can see in ANSYS FEA, but a very informative solution output can be arrived if you use the code that I have provided in the manual of your FEA lab. Okay, and also, like I said, I used the codes and the problem from this particular book, MATLAB Codes for Finite Element Analysis. It's a Springer published book by AGM Ferreira. So you can use this book for finding different codes on all the FEA problems that you have. Okay, so whatever you have done in your class, all those trusses, 2D frames, 3D frames, all these things you can do it on MATLAB as well. Then they have given you several codes with examples for doing that also. So make sure you try this out as well. And also, you do know that MATLAB is software that our institution has purchased, and we have every student has a license for it. If you don't, please you can get back to me or Shivakumar sir, and we'll be able to help you get that as well. So with that, we are ending the FEAL lab sessions. I hope you really learned a lot, and I hope you continue to learn more by reading through the book and trying out these problems on your own. So thank you.